Today we will think about path integral formulation. So let's assume that the classical particle's trajectory can be represented in xt plane. So we are starting with t1 and x1 and ending with t2 and xb, let's say xa. So somehow the classical particle will pass through this trajectory, but in quantum mechanics says we are not sure about the path, and we can only tell about the probability amplitude. So assuming that the quantum mechanical particle will pass the following path, and then we can divide the time interval by many small intervals. So this will be the path for the classical particle. And we are not so sure about the quantum mechanical version of a path. So we are going to develop the series of lectures to cover this path integral formulation. So assuming that the ordinary particle in one dimension satisfies the following Hamiltonian. So ordinary particle in one dimension is given by the following Hamiltonian: p squared over 2m plus 3x. And path integral is about the probability amplitude. Path integral is about the probability amplitude. So suppose we know that the particle was at t1 x1 and later on at t2 x2, and we would like to find out the probability amplitude to go to x2 at t2 from x1 at time t1. So let's assume that x1 is a state of particle for the particle at x1. Then x2, x1 will be the probability amplitude as covered in the previous lecture. To be at x2 if we know that a particle was at x1. And we assume that classically x2 and x1 will be given by delta function x2 minus x1. And let's assume that let x hat will be the position operator such that x is given by this eigenvalue problem, Then the time dependence with the time dependence is given by Heisenberg operation. So x is given by x t equals 0. Then t is given by this Heisenberg operator form. The time-dependent state is given by the following. Heisenberg eigenstate is given by I h t over h x 0. Then obviously xt is given by xt. Then obviously xt2 x1 t1 is not delta function unless t1 is t2. The above eigenvalue property can be shown by the following way. xt is given by exponential I h t h x 0 exponential minus h t over h, and xt is given by exponential I h t over h x 0. So exponential I h t over h x 0 x 0. Then obviously I h t over h x 0, and this x is just a number, so you can be putting out of the operator. So x exponential I h t over h x 0 is nothing but xt. Then x2 t2, the probability amplitude x1 t1 is given by x2 0 exponential minus h over h bar t2 minus t1 x1 0. So the actual path will be something like that. If we divide by the two intervals xa, ta, tb, and if we divide by many small intervals, this is xa, starting with xa, starting with xb. So we can divide by something like this. So this is xb. We can interpret the following way. So xb, the probability amplitude between particle, oh sorry about this, this must be comma, xa ta is given by xb 0 exponential minus I h over h bar tb minus ta xa 0. Since the quantum mechanical eigenstate form a complete set of a Hermitian operator, the probability amplitude between B and A can be written by the following way: B, C, C, A, where C is 1. We can extend this into continuum state such that summation become integration, so x over x can be 1. So what happens to time dependent state? Then dx xt becomes exponential minus I h t over h bar x exponential I h t over h bar. It becomes exponential minus h bar t over h bar from integration dx x exponential I h t over h bar. But however, the center become identity operator, so this is exponential minus I h t over t I exponential I h t over h. It becomes I. So let's divide the interval by n plus 1 division. So say this is t, starting with the ta and tb, we divide by 1, 2, 3, 1, 2, 3, n. So it's going to be n plus 1 division, and this small interval is epsilon. Then we can say that tb minus ta is epsilon times n plus 1. Then xbtb xata is the sum of many different integrals, tx1, txn, starting with xb, tb, xn, tn, xn, tn, xn minus 1, tn minus 1, xn minus 1, tn minus 1, x2 t2, x1 t1, x1 t1, xa ta. So the probability amplitude, oh sorry about this, I'm making a mistake again. So xk tk, what am I doing? The probability between xk tk, xk minus 1, tk minus 1 is nothing but xk exponential minus h bar tk minus 1 xk minus 1, and this xk exponential minus I h epsilon. So this is epsilon over h bar xk minus 1. Is 2m over p squared plus 3x. P is given by minus h bar over. So you can refer to my previous lecture, Applied Quantum Mechanics 3. Then x over p any state is given by minus I h bar partial x psi, or xp is minus I h bar partial x xp is p over p. we assume that there is eigenvalue relationship. So partial xp becomes ip over h xp, and solution of this can be written by x over p is some normalization constant c times h over p x xp. Then xp px prime will be given by c square exponential ip over h x minus x prime. So consider following the probability amplitude minus infinite to infinite dp xp px prime will be given by c square absolute square of c minus exponential ih over p x minus x prime dp. We know that exponential ixt dx is 2 pi delta t. So if we set c as 1 over square root of 2 pi h, then xp px prime will be delta x minus x prime, which is x and x prime. So we also have the following properties. dp pp is identity. Then we can say that from this we have the following properties. 1 over square root of 2 pi h exponential I px over h bar. Before we continue, let's consider the following operator algebra. The useful operator algebra. So from now on, you're going to omit the hat. So we are going to omit tilde or hat to represent an operator. So first of all, the following operator form: a, b, exponential minus lambda a. So this operator can be represented, expanded by the Taylor series: 1 plus lambda a exponential lambda square over 2a square blah 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 b 1 minus lambda a plus lambda square over 2 a square blah 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 is given by b plus lambda a b plus lambda square over 2 a square b plus blah 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 1 minus lambda a plus lambda square over 2 a square minus, so it can be written as the following way: lambda ab lambda square over 2a square b blah 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 minus lambda ba minus lambda square aba plus lambda square over 2 ba square plus blah blah blah. But together as the following form: b plus lambda ab minus ba plus lambda square over 2 a square b minus 2aba plus ba square blah 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 So this is b plus lambda ab minus ba plus lambda square over 2 a square b minus aba minus aba plus ba square plus blah blah blah. So this is nothing but b plus lambda ab plus lambda square over 2 a ab minus ba minus a b minus ba a b plus lambda a b plus lambda square over 2 a b minus a b a is nothing but b plus lambda a b plus lambda square over 2 a b blah blah blah. And this formula is named called Baker-Campbell-Hausdorff formula, and will be very useful. Second identity is the following. So assuming that we have the following operator function given by exponential lambda a exponential lambda b, and you differentiate by, okay, this is actually a function of lambda. d lambda dfa is a exponential lambda a exponential lambda b plus a exponential lambda a b exponential lambda b. So this is f lambda. So this is a f lambda plus, we can modify the following way: lambda a p exponential minus lambda a, and then exponential lambda a exponential lambda b. Again, this part become fa, and then for this there is no a here, right? No a here. So we can apply Baker-Campbell-Hausdorff formula for this box. So a f lambda plus, we have b plus lambda a b plus lambda square over 2 a b blah 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 f lambda. Assume that commutator is non-zero, but the second commutator is 0, then we have the following formula. Then d lambda d f lambda is equal to a plus b plus lambda a commutator b f lambda. The solution will become is equal to exponential a plus b lambda plus lambda square over 2 ab is exponential lambda a, exponential lambda b. So if we set lambda equal to 1, then exponential a plus b becomes exponential a, exponential b, exponential minus 1 over 2 ab. So we will stop here today and then continue next time.